Good afternoon. The broadcast has started. All attendees are in the listen-only mode. My name is John Carville. I'm a Director of Aber Instruments Limited. Welcome to the webinar presented by UMass and organised by Aber Instruments and Applicon Inc. in USA. The talk is entitled The Improved Estimation of Viable Cell Density Using Dielectric Spectroscopy. The principal speaker today will be Dr. Seong-Kyu Yoon of UMass Lowell. The webinar will last for approximately 45 minutes, and this will be followed by a question and answer session at the end of the presentation. The webinar is interactive, so please feel free to type in your questions as the session progresses. The event will be recorded and will be available for download at a later date. If you require a copy of the slides, please contact myself or John Poppleton, the Product Manager at Applicon Inc. Alternatively, you can reach me via the contact page at the Aber Instruments website. Now I would like to begin the formal presentation with a few slides about Aber Instruments, the development of a biomass monitor for mammalian cell culture, and how products are distributed across the world. Aber Instruments is located in the town of Aberystwyth, which is on the west coast of Wales in the United Kingdom, overlooking the Irish Sea. The technology for measuring the online cell concentration in bioreactors originated about 25 years ago as a spin-out company from the University of Aberystwyth. Although the first biomass monitors were aimed at the emerging biotechnology market, it was actually the brewing industry that initially adopted the technology. In the case of the brewers, the probes are used to accurately dose the exact amount of yeast into each fermentation and are now a standard in virtually all the main brewing groups worldwide. Customers include Anheuser-Busch, which is now AB InBev, Coors, Heineken, Guinness and Carlsberg. The probes are now being used in microbreweries, and those in USA might recognize names like Dogfish Head, Deschutes and Sierra Nevada, who use the Aber Instruments yeast monitor. The first dedicated instruments for cell culture were manufactured in 1995, and today over 500 systems are used in cell culture applications, with some companies using over 50 systems in CGMP applications. Aber Instruments is an employee-owned company, and since 2012, and our products are primarily sold through an international distributor network. In North America and Mexico, our exclusive distributor for biopharma applications is Applicon Inc. In the presentation that follows, one of our older generations of instruments, the Model 220 biomass monitor, was used for the experiments. Although this instrument is still available, it's been superseded by the Futura range of biomass monitors. This range includes options for smaller bioreactors where there's a limited head plate access and a single-use probe for disposable bioreactors. The principle of the operation will be covered by our next speaker. Finally, there will be another seminar on the 12th of February presented by Bend Research. Registration for this event can be made via both Bend Research and Aber Instruments websites. I would now like to introduce to you Dr. Seong-Kyu Yoon. Dr. Yoon is the co-director of the Massachusetts Biomanufacturing Center and assistant professor in the Department of Chemical Engineering and Biomedical Engineering Biotechnology program. Dr. Yoon's research area is systems biology. Research covers multivariate data analysis and chemometrics in life science. He is currently developing a systems tool which will explain the variability to productivity and quality of CHO mammalian cell culture product. Before joining UMass Lowell, Dr. Yoon worked at Biogen IDEC, leading the process analytics group of manufacturing sciences. He implemented multivariate statistic process control to all unit operations of both commercial and clinical manufacturing. And now, without further ado, I would like to hand over the microphone to Dr. Yoon.
All right, thank you, John. This is Song Ki-yoon. Can you hear me well, all? I hope you
Yes,
guys can hear me
you can
well.
be heard extremely clear.
Okay. I'm Song Ki-yoon. I'm from University of Massachusetts Lowell, which is about 20 miles north from Boston. And those of you who's in United States, it's a good morning, and those people in Europe, good afternoon. So today, what I'm going to talk is about the dielectric spectroscopy and chemometrics technology for monitoring mammalian cell culture this growth and its productivity monitoring. So today, talk that I'm going to have, first of all, I want to explain briefly basic principles of dielectric spectroscopy and what are the challenges most of the biopharmaceutical companies are facing with this technology. And as part of the solution and fixing the challenges, we have studied a few alternative options. So I'm going to explain what are the core mechanistic explanation of the problem, what is the reasonable way that we can overcome those. And one of the key approach that we have we studied, is to use multivariate regression modeling of dielectric spectra for biomass estimation. So I'm going to get into a little bit more detail about that. What is the justification, what is the good reasoning of this technology with dielectric spectroscopy. And then after I cover some of the research outcome shared, and then I'm going to see a little bit a few possible options that you can expand this technology for your application and your work. And then I'm going to wrap up the presentation. And first of all, before we get into dielectric spectroscopy technology for biomass estimation, I want to briefly mention that what are the technologies available for measuring viable cell density. And in biopharmaceutical industry, that viable cell density and cell viability, those are the measurements usually available on offline basis. So CDAC and ViCell, and there are multiple choices that you can measure those viable cell density and cell mass. And last several years, including this Aber's new technology that we're going to be covering today, and a few alternatives came out. And about 2 decades ago, the near-infrared spectroscopy came on as the first technology. And then after that, a few other soft sensor-based approach came out, and that was used for estimating oxygen uptake rate, and the CER is a carbon dioxide evolution rate, or some of the nuclear magnetic resonance based technology that people are trying to say that some of the cell metabolics and all the information can be measured. So basically online and offline technology, but for the future application for statistical process control and monitoring, those real-time technology became pretty important and promising for many applications, especially biopharmaceutical industry. All the unit operation is a batch-based, but in next 5 years, there's a huge initiative and tendency. All the batch processes might be converted into continuous processing. Then, in conjunction with the process analytical technology and quality by design initiative by FDA and European agencies, I think those real-time technology will be pretty significant, way more significant compared to the current status. So this online technology is the one that we're going to be focusing on today. And the technology we are focusing here is called dielectric spectroscopy. And as you know, this technology was initiated from the Aber Instrument. I'm not going to get into too much detail, but I'm just going to explain what's the principle. So when cells are placed in the presence of alternating electric field, a polarization is going to be developed at the pole of the cells. And those magnitude of this charge separation can be measured by the capacitance of the solution. And then those capacitance difference is going to be used for estimating viable cell density and biomass and so on. So that's the fundamental principle. So as John outlined, there are many companies in the United States and Europe using this technology for estimating the viable cell density in real time, and then use that for the decision for harvest and the product transfer from seed train to the product train and so on. But however, the limitation or one observation made by the several companies are during the lagging and exponential growth period, this real-time estimation based on this dielectric spectroscopy is pretty good. However, as you see on the right upper corner, that B29, this red line, those are the real-time estimation based on this dielectric spectroscopy. And then blue diamond, those are the offline viable cell density measurement. And as you see, beyond this plateauing period and then declining phase of the cells, there's some deviations between real-time estimation and offline value start to become significant. And this is a quite commonly observed this situation by several companies, and there was so many conversation and observation and discussion, why this is happening. So this is the main focus of this presentation. Starting this point, we started investigating why this is happening and what would be the remedies and what is the technologies that we can use for as a future technology. So this presentation was actually the scanned copy of the presentation made by the Millipore scientists 2 years back at one of the conferences. To share with you some objective observation, I just copied from the presentation with the permission of the scientists. Present this one. Okay. So a little bit more detail that how the viable cell density can be measured. So fundamentally, all the mechanism is based on a beta dispersion curve, which is the Cole equation. And as you see on the left-hand side in the figure, that the x-axis you have a frequency, and the y-axis you are measuring capacitance in pico the unit. Then from this chart, usually you are measuring two quantities. The first one is the delta epsilon, which is the difference between the baseline and the capacitance value at the specific frequency. So delta epsilon value is going to be measured from this. And then the middle of the curve, there is FC, which is the critical frequency. So those two quantities are measured from the instrument. And then based on that, we assume the Cm, sigma I, and sigma A, those are the conductance in the media and the intracellular the material. So based on assuming those Cm, sigma I, and sigma A, with the measurement of the delta epsilon and Fc, based on the equation that is shown on the right upper corner, we are estimating viable cell density and then radius of the cell. So those viable cell density estimation and radius are pretty good, as I said, during the lagging and exponential growth period. However, it's becoming pretty quite significant amount of deviation during the declining and after plateau period. So first of all, we were wondering why this is happening. So we first checked the radius. So based on the value measured by this technology, we monitored radius calculation based on this equation and based on the capacitance measurement. And we found one thing very interesting. So we replaced this radius measurement by the offline measured value. And then we have seen quite significant amount of oscillative calculation. So we replaced that in the core equation, we replaced radius estimation with the correct measurement, which was quite continuous. And then we look back the vibrant cell density and the capacitance correlation. And in this slide, as you see on the left-hand side, you can see the correlation between the vibrant cell density and then capacitance value. You still see quite clear two very distinct characteristic. So which was mainly caused by the oscillative estimation of the radius. And after we replace that measured radius value, calculated radius value with the measured value from the offline instrument, we see the correlation plot and regression plot between the capacitance and the vibrant cell density again on the right hand side. And still, as you see at the lower corner, you see quite clear the merging in the one consistent numbers. However, even if you have calculated one single line, which was based on the data point from the up to the plateauing period and after the plateau period, you still see quite a significant amount of deviation at the upper corner. That means after the plateau period, during the declining phase, even if you have correct radius measurement, you still see quite significant amount of deviation. So out of this observation and this investigation, we concluded still there are some fundamental things that we need to fix for the vibrant cell density estimation, and that's just calculated value based on the capacitance value. So we thought we need to do a little bit further investigation how the capacitance values are going to be coming up. So before we get into too much detail, we collected all the capacitance value, this radial dielectric spectra, full spectrum over the cell, the growth cycle. And on the left upper corner, this is the chart based on the principal component analysis that can be that can give you a pretty good overview of what's going on. And as you see, all the dielectric spectroscopy, put it into the principal component analysis framework, then you can see at least there are 4 distinct clusters. And one cluster was made by the exponential growth period, that is the left bottom corner from the plot. And then the right bottom corner, you see the stationary phase, and then eventually you are going through the declining phase. And this clustering represents that in the dielectric spectroscopy measured over the whole full cell growth cycle, you are experiencing at least 3 or 4 distinct changes of the dielectric spectroscopy pattern. So that means even if you measure the dielectric spectroscopy value at specific wavelengths, that may not be capturing all the information that's going through, all the physical phenomena that you are having. So on the right upper corner plot, we have 2 the calculated principal component. And as you see, the red line, which is the first principal component, and blue line is the second principal component. Those are the most distinct and obvious variability observed from the dielectric spectroscopy. And as you see, the first principal component is almost the same as the dielectric spectroscopy pattern. And the second one, at the low frequency region, you have pretty low value, and then they're increasing around the next corner frequency region and then going down. So those are capturing another physical behavior. So to figure out, to further detail how things going, we applied further the multivariate statistical method. One of them is called evolving factor analysis. And this methodology is going to calculate eigenvalue and eigenvector with the data set given. So we have done two different type of factor analysis. One is the forward factor analysis, and the other one is the backward factor analysis. And methodology is pretty simple. In forward factor analysis, it's going to calculate eigenvalue and eigenvectors while increasing number of observations. So starting from day 0, you calculate eigenvector. Then every single day you calculate eigenvector again. So eventual goal is to calculate what are the distinct changes you are experiencing from the cell during the cell growth period. So at the bottom, left bottom corner, and those are the viable cell density value changes of the few batches. And as you see, most of them have exponential growth period and plateauing and declining. And then left to upper corner 2 chart are the eigenvalue changes based on forward factor analysis and backward factor analysis. And as you see, this eigenvalue trend has a quite significant the meaning for us. So you can see that at the left corner, those are the seeding, and then exponential growth period, and declining phase, and abrupt decrease in the viability. So all those cell growth cycles can be captured quite well based on this the factor analysis, but which is based on full spectrum of the dielectric spectroscopy. And this indirectly indicate that we may need to monitor, we need to look at whole spectrum instead of the dielectric spectral value at the specific frequency. So, and then we look through the why this is happening, why this dielectric spectral value, and then based on that, capacitance values are going to be changing. So we look into the cell morphology and biology aspect a little bit further. And as you see, as you know, that what's happening after plateauing period and declining phase, a lot of apoptotic cells are being created, and as a result, those guys are increasing the conductivity and the extracellular properties in the media. And also, as part of this apoptotic process, the compositional changes are going to be caused as well by having more culture growth and depletion of the glucose and glutamine and so on, and also accumulation of the lactate and ammonia. All those are causing compositional changes. And also, at the same time, cell morphology is also changed, and such as the diameter and the membrane capacitance and internal conductivity. So those all biological changes in the bioreactors. We need to capture them all somehow by dielectric spectroscopy. And then based on this slide and the previous slide, this is justifying why we need to look at whole spectrum instead of dielectric spectroscopy value at the specific frequency. So based on this justification, we decided to look at the full spectrum. Then what is the methodology that we can look at? It's a multivariate statistic. And many of you might be familiar with this multivariate statistic. And here I want to give you a little bit of the explanation of what it is. So usually this principal component analysis and partial least square, those are the linear system-based technology. So usually partial least square works very well in giving regression model between input and output data for the linear system. So in this case, all the input data is going to be dielectric spectrum, and then output data will be the offline viable cell density. So we are finding regression model. But here, the one thing that we are experiencing is that during the exponential growth period, we have its a correlation structure. And then during the declining phase, we have totally different correlation structure between dielectric spectroscopy pattern and the viable cell density and cell viability and so on. So linear system technology, we can see that immediately this may not work well covering whole cell growth the curve. So we may need to have two different partial least square regression model, one during the exponential growth period and then one during the declining period. But there is a technology that multivariate statistical analysis regression methodology that you can apply to the nonlinear system, which is our case. So one of the nonlinear methodologies called Cornell PLS, which is the regression methodology that you can apply to the nonlinear system. And then the other one is called locally weighted partial least square. This is one of the methodology that you can apply to the nonlinear system as well. However, in this case, partial least square model is going to be built based on a piece of data set, but your data set is being updated. For example, first few days that you are your regression is based on the data set up to day 3, and then day 4 you are making the regression model based on day 1, 2, 3 and data set. And then at the day 5, you are estimating your data set based on the data set collected from the day 3, 4, 5. So this way, you are moving your data set for the regression, but by doing that adaptive and data set, you are able to adapt correlation structure change. It means that when cell is getting into the plateauing period and declining phase, somehow we can take care of those morphological changes in our model. So we tried those 3 different types of methodology to take into account fundamental changes during the cell growth and declining phase. And we tested those 3 different types of model, and as you see from the chart that training data set and validation data set, those methodology, red solid line is based on the locally weighted partial least square regression, and then square, which is the offline viable cell density measurement, and locally weighted methodology is giving the best the matching performance. So this model is very different from the earlier model. Here that there are 2 distinct differences between previous approaches and this. And number 1 is that we are using whole dielectric spectroscopy, the spectrum, and the second, we are using a locally weighted and adaptive regression methodology. So those 2 are the distinct changes from the previous methodology. And based on this locally weighted regression model, and also nonlinear model and regular PLS model, we calculated viable cell density value real time. And if you see again, this real time performance is also displaying, demonstrating the locally weighted methodology is giving the best performance. Okay, so that's our sort of summarizing slide that's demonstrating all the research work we've done so far. And then based on this good matching the result, we thought about what might be the possible extension of this proposed approach. And number 1, that current dielectric spectroscopy technology, its application was sort of in some sense limited. For example, for the harvest decision, usually harvest is going to be made when cell viability goes down below the 70% or 60%. So meaning that harvest is going to happen during the declining phase. But since that dielectric spectroscopy and capacitance-based viable cell density measurement is not going to be giving accurate numbers, so this technology hasn't been used for the harvest decision. But based on this improvement, this technology might be able to utilize for this harvest decision, as well as other the monitoring the key changes in the bioreactor operation. And also, this technology might be able to utilize for detecting cell, the apoptosis and metabolic shift, the observation as well. And also, as I said, this technology can be very well utilized as a tool for making harvest decision. And also, right now the bioreactor operation, literally, the very little amount of control concept is introduced, except for the dissolved oxygen, pH, and temperature, and the flow rate sparging. But there isn't any control methodology that you can really control the viable cell density or specific titer and so on. But there are a lot of research groups who's working on this batch control methodology. But this real-time viable cell density measurement is going to contribute significantly that batch control methodology for the bioreactor. And also, lately, we're looking into this dielectric spectroscopy data with near-infrared information, if there is any complementary aspect between those two few different spectroscopy technology. And lately, last few years, RAMAN spectroscopy has been very popular for many several biopharmaceutical industry. But we see some complementary aspect with the RAMAN spectroscopy and this viable cell density measurement based on this capacitance value. So that's the current research topic we are conducting. And to summarize what we have presented so far, and the first one, due to the complex time varying dynamics of the dielectric spectra, most of the biopharmaceutical applications are facing that this technology is being utilized in a limited fashion. So based on that, some of the observations we made an assessment that we need to look at the full spectrum instead of the spectral value at a specific frequency. That's the second observation we made. And the third, partial least square methodology is a linear system-based technology, but due to the fact that cell growth is going through the nonlinear pattern, so we need to utilize the nonlinear version of the partial least square method, regression method. And then locally weighted partial least square methodology based on our simulation study has demonstrated their best performance. So incorporating this methodology into the current application that you guys are using, this dielectric spectroscopy can give you a significant amount of improvement and opening the door for other applications. So this is summarizing what I presented today. So this work, first of all the work was done by my research group. It's a systems biology group. And we have the collaboration and support from Massachusetts Life Science Center and Sigma Aldrich, and Aber, Pfizer, Millipore, and Vertex. And also at the University of Massachusetts, we have Biopharmaceutical Consortium that I have one slide the next. It's also sponsoring our research group. And also University of Massachusetts science and technology funding was also part of our funding source. I really appreciate all the collaborator and then supporter, especially Aber, applicant for this project. So before I finish up and open for question and answer, I'd like to have one slide which is about a second biopharmaceutical summit that we are planning in May. The last year, we had the first summit in March 2012. We had about 150 people from most of the biopharmaceutical companies and system suppliers and so on. We talked about technologies and challenges in the biopharmaceutical industry. And this year, we are planning to have second summit in May with the topic of continuous bioprocessing. So more detailed information is going to be available, and if you have any question and you would like to participate as a speaker or as a attendee, then you can feel free to email me or call me. So thank you for your attention, and I'll be very happy to answer any questions coming up.
Well, thank you, Dr. Yoon, for an absolute excellent presentation. Just to comment on the very last slide, I personally attended the first Biopharmaceutical Summit last year, and I think it was one of the best events of the year. And as Dr. Yoon said, there was up to 150 people attending that event, so please come along to that. So we just have time for maybe one or two questions. I've got one question here. Could Dr. Yoon or Dr. Carville speculate if the Aber probe is measuring apoptotic cells or not? Dr. Yoon, if I could ask you to comment on that.
Yes, I had one slide that's indicating we can measure apoptosis of the cell and some compositional changes. We do not directly measure those apoptosis, but based on dielectric spectroscopy pattern and spectral shift, that we will be able to measure that indirectly that apoptosis in the cell.
Okay, if I could just make a few comments on that as well. There's 3 research groups looking at this same aspect at the moment. So as well as UMass Lowell, we have Bend Research and the University of Manitoba. According to the University of Manitoba, things like the SEDEX or Vicel actually overestimates the viability by not recognizing apoptotic cells with an intact membrane, but it's actually rather dependent on gross membrane damage which occurs at the late stage of apoptosis. They've actually speculated that the Aber is actually measuring the total viable cells plus the cells which are in early apoptosis, and then a fraction of the cells which are in mid-apoptosis, while the SEDEX tends to measure mainly the viable cells and maybe just a proportion of the apoptotic cells. So that's really from the work of the University of Manitoba. Is that something that you agree with, Dr. Yoon?
I think so. So just to add one more comment, at the UMass Lowell in my research group, we are looking into the metabolic flux balance analysis, and we're trying to match up that metabolic flux balance real time to the dielectric spectroscopy. So by measuring a metabolic balance in the cell culture and bioreactor, we can have more direct indication, we apoptosis is coming out. And then by matching that to dielectric spectroscopy, we're hoping that we can clearly indicate whether this dielectric spectroscopy is able to measure apoptotic the process in the cell culture process. So that's one of the ongoing projects we're conducting right now. And I will be able to share some observation in a few months.
Okay, I think that's probably all the time that we have for in terms of the questions today. There are a few more questions which have been posted on our panel list at the moment, but we'll be able to respond to those privately. So thank you very much for anyone who's actually asked questions today. So with those final words of thanks to University of Lowell, I'd like to formally end this webinar.
All right, thank you.